So now that we are comfortable drawing Lewis dot structures and from those structures evaluating the shape of the molecule, we can start predicting what will be the properties that those molecules will have, especially those properties that depend on shape. And one of those properties that depends on shape is polarity, and it's a very important property. It gives a lot of information about what it will do. Before we begin talking about the polarity of the entire molecule, we need to start talking about the polarity of a bond. So this is an individual bond. So a covalent bond between two atoms. And a nonpolar covalent bond is defined as a bond where the electrons are shared equally. Remember, when an atom shares an electron, what it means is that it orbits one atom sometimes and then another atom the rest of the time. So that would mean that it would spend equal time on both of those atoms. The property that can tell us whether the bond is polar or nonpolar is electronegativity. So just as a reminder, electronegativity is the pull or force of attraction of an atom for the electrons in a bond. Fluorine's the most electronegative. It was a periodic trend that we looked at, and we'll look at another table of it in a moment. A nonpolar bond is where the electrons are shared equally, so then a polar bond is where the electrons are shared unequally by the two atoms, meaning that the electrons spend more time around one atom, specifically the more electronegative atom. And if you take a look at the diagram, you'll see that there's a diagram of a bond between hydrogen and chlorine. And you can see that the hydrogen is like a gray, the chlorine is a green, but the chlorine's green is sort of bigger. And what that's representing is the fact that the electrons in that bond spend more time around the chlorine. And you can see I drew in there the electronegativity values of those two elements. Chlorine's electronegativity is higher than hydrogen. That means those two electrons that the chlorine and hydrogen share will spend more time around chlorine than they do around hydrogen. The next page shows you the table of electronegativity values. You never need to know these values, like the numbers, like we would an atomic number or molar mass or something like that. You won't even have to look them up. I did point out that, for the most part, low electronegativity values are the metals. The higher electronegativity values are the nonmetals, with the three highest electronegativities being fluorine, oxygen, and nitrogen. That's going to be important in a few videos down the road. And remember that the noble gases have no electronegativity values listed because they don't make bonds. So then how can we tell whether a bond is polar or nonpolar? Well, we can compare the electronegativity values. And if the electronegativity values differ, we can actually find the number that can tell us whether the molecule is polar or nonpolar. So you can see the example here, the electronegativity of chlorine, 3.16, where hydrogen is 2.20. The difference is 0.96. That means that bond is polar. And we can see this symbol again, the partially negative symbol around the describing the more electronegative atom, and the partially, remember it kind of looks like an unfinished 8. The partially positive symbol is on the hydrogen atom. And then this table down here helps us to understand how do you know? And the table gives you actual numbers. Now, those numbers you do not need to know because different textbooks will actually define polar versus nonpolar as different numbers. And there's actually more than one table of electronegativity values. So we break it down really simply by saying if you have a molecule in which the two atoms are the same, chlorine to chlorine, hydrogen to hydrogen, oxygen to oxygen, then they will share those electrons equally, and that bond is nonpolar. There is an exception to that, and that is carbon to hydrogen. And it's actually a really important exception because carbon to hydrogen is a super common bond. You probably remember in bio talking about lipids and the phospholipid bilayers. Those are all carbon and hydrogen bonds. Those two atoms, even though they have a slightly difference in electronegativity values, the fact that hydrogen is so much smaller sort of makes up for that. So they do in fact share electrons equally. So nonpolar bond, two of the same atom, or carbon to hydrogen. A polar covalent bond, we're not going to break it up as this table does with kind of polar or really polar. We're just going to go with polar. It's two different nonmetals, with the exception of carbon to hydrogen, which is nonpolar. So any two nonmetals, carbon to chlorine, oxygen to fluorine, all of those are polar. And then the last category is ionic. Ionic happens, we talked about this, when the electronegativity difference is so big that the metal completely gives up its electron to the nonmetal, and then the nonmetal is positive, the nonmetal is negative and the metal is positive. And so that happens between a metal and a nonmetal. So we know metal, nonmetal, ionic. Two nonmetals, it's definitely going to be covalent. It could be nonpolar covalent or polar covalent. The difference is, are those two of the same element or are they two different elements? This brings us to the relationship between a polar bond and a polar molecule. A polar bond doesn't really matter all that much by itself. What it does is it helps us understand polar molecules. So this is a little different, more sophisticated vocabulary for this. Definitely more sophisticated than you used in bio. So you can see the Y part. The polarity of a particular molecule is important in determining how that molecule interacts with other molecules around it. It's going to give us solubility, melting point, boiling point, all sorts of stuff. So the bond dipole, that little box over on the left, a bond dipole is just that's a way to talk about the polarity of a bond, whether a bond is polar or nonpolar, right? A single bond can have a bond dipole. That's the exact same concept as a single bond can be polar. The bond dipole is a measurement of the electronegativity difference between the two bonded atoms. This is a measurement of how unequally the atoms, the two atoms, share electrons, and the bonded dipole arrows point towards the most electronegative atom. So you can see over here on the right-hand side, right, we have an oxygen-hydrogen single bond. The oxygen is more electronegative than hydrogen, and so we have the delta negative sign and an arrow pointing towards oxygen. That's symbolizing this bond dipole. This bond dipole, you can actually get a number for it that we don't do, but it can get much more sophisticated than this. And then what the heck do we do with bond dipole? Well, that helps us to understand a little bit better what a polar molecule is. A polar molecule is defined as if a molecule has polar bonds and it is not symmetrical. It will have a dipole moment and it is called a polar molecule. A polar molecule, if you look over on the right-hand side to the dipole moment, right? The molecule dipole moment is a net dipole moment representing all of the bond dipoles. It's sort of summing up all of the polar bonds together and looking at, in this molecule, is there a region of negative charge and a region of positive charge? Or are the electrons evenly distributed in the entire molecule? So not just the bond, the entire molecule, right? A dipole moment is a measure of the separation of opposite electrical charges. Molecules with a dipole moment have areas that have a partial positive charge and partial negative charge. If you look at the example here, the example is the water molecule. We know water is polar. You've been talking about that since middle school. This is just a little bit more sophisticated of a discussion as to why water is polar. First of all, water is polar because it is bent. And because it is bent, you can see that those two bond dipoles point towards the same area. They both point up towards the oxygen. That means that the electrons spend more time around the oxygen atom. That means that that oxygen atom is partially negative, the hydrogen side of that molecule is partially positive, and that is a polar molecule. If a molecule has only nonpolar bonds, then the molecule itself is nonpolar. This is most of those hydrocarbons that you studied about in biology, those lipids, those fats. If a molecule has polar bonds, but those polar bonds are symmetrical, so that the direction of the dipole moment, the direction of those bond dipoles cancel each other out, then you can have a molecule that is nonpolar but contains polar bonds. So the first example, Ch4 methane gas, you can see those bonds are nonpolar. So that no matter what, that's a nonpolar molecule. If on the bottom right-hand side, you can see carbon dioxide. Carbon dioxide is also a nonpolar molecule, but it contains polar bonds. You have the oxygens pulling the electrons to the left and the other oxygen pulling the electrons to the right. And it's like a tug of war where both sides are pulling equally. So those electrons spend more time on the oxygen, but because those two oxygen are symmetrical with each other, then the molecule itself has a zero dipole moment. It is non-polar. The next slide just shows a couple different pictures of water to help just hammer home that water is a polar molecule. So you can see the arrows pointing towards the more electronegative element, and that the bond, the overall dipole moment, the overall polarity of the molecule is such that oxygen has more electron density. Those electrons spend more time around the oxygen. You can also see it in that shaded, colored diagram, that space filling model, where red is where the negative charge is. And you can see that's definitely centered around the oxygen atom. So then how can we tell? So you might want to pause the video for a second and just copy down this flow chart. And then I'm going to explain it, or let me explain it and then copy it down. So this is a flow chart, which means these are sort of the questions that you ask yourself. When you are asking yourself, is this molecule polar or nonpolar? The first question you ask yourself is, are there lone pairs on the central atom? If there are lone pairs on the central atom, 99% of molecules with lone pairs on the central atom are polar. So you go all the way to, yes, there are lone pairs on the central atom. It's almost always polar. And you can see the examples there are water and ammonia, H2O and NH3. The exceptions to those are where the lone pairs themselves are symmetrical with each other. And that happens when you have a linear molecule with 5 electron domains. So 5 electron domains, 2 bonds, 3 lone pairs. That's linear, but look at those electrons. They are all in that equatorial position. They are positioned 120 degrees apart. They pull, those electrons are spread out evenly. So that's actually a nonpolar molecule. The other example is that Xenon Tetrafluoride. That's a square planar molecule. Again, those, the square planar molecule is flat. So there's a xenon and 4 fluorine, and then an electron cloud on the top and an electron cloud on the bottom. And since those electron clouds are exactly symmetrical with each other, that molecule is nonpolar. On the right-hand side, you can see the second question you ask yourself, which is, are the outside atoms the same or different? If the outside atoms are the same and there's no lone pairs on the molecule, that means that those this is like the carbon dioxide example, where those atoms may be pulling the electrons away, but they're all pulling symmetrically and with the same force, with the same amount. If all the outside atoms are not the same, then that is a polar molecule. You can see that example with HCN. Right? There's no lone pairs on the central carbon atom, but one side has a nitrogen and a lone pair. And the other side is a hydrogen. Well, nitrogen has a larger electronegativity than hydrogen, so the electrons are pulled towards that nitrogen atom. We could say that this side of the molecule is delta negative and the hydrogen side is delta positive. Right? The molecule will be delta negative on the side where there are more electrons or where there are more electronegative atoms.